Next, we discuss the second solution, that is the graphical method. Taking a simple circuit containing a nonlinear resistor as an example. This is very similar to the example we used in learning the substitution theorem previously. We can draw their UI features in the same port. For the left, we can write U equals minus R1 times I plus US. For the right, of course, it has a nonlinear relationship. We assume that it is the current controlled type, that is U equals Fi. So in the same UI plane, we draw the UI features of the left first. Its intersection with the horizontal axis is US, and the intersection with the vertical axis is US over R1. We have discussed this previously. Then we draw the nonlinear relationship. Assume it is such a shape. We find the intersection point is the working point we defined before. Here we give it a more accurate name, the quiescent point, or Q point for short. The meaning of the quiescent is static state or static. So there must be dynamic. There will be some disturbance around the quiescent point. We will introduce these circumstances in the next few lectures. It is the simplest case we discussed just now. If such a nonlinear resistor is connected with a complex one-port network which contains independent sources, dependent sources, and linear resistors, what do we do? If you can remember that seeing from here to the left, they can be equivalent to a Thevenin circuit, that means your previous study is effective. Yes, for the left one-port network, we can substitute it with a Thevenin circuit consisting of UI and OC and RI. Then we got an equivalent circuit like this. So the graphical method can still be applied. Next, let's sum up the characteristics of the graphical method. It has two steps. In general, we first need to look outwards from the nonlinear resistor. Other parts can be substituted by the serial connection of an open circuit voltage and the internal resistance by using the Thevenin theorem. Secondly, under the same definition of the port voltage and current, we draw their features curves in the UI plane. The intersection point is the Q point. So we finish the whole analysis. This approach has its advantages. First, it's very simple. Secondly, it's intuitive. And this intersection has the obvious physical meaning. About the physical meaning, we will continue to discuss later. But it also has obvious shortcomings. First, it sacrifices the precision, because all the values come from the figure, so they have reading errors. In addition, you might notice we can use the Thevenin theorem because seeing from the nonlinear resistor to the left, it is a linear subcircuit, so it is only applicable to the circuit containing one nonlinear resistor. This is another drawback of this approach. Okay, that's all for this lecture.